The fastest recorded lateral movement in a real intrusion last year was just 2 minutes and 7 seconds. Your SIM ingestion pipeline takes longer than that to normalize a single log. If you think detection engineering is just writing better SIM rules, you've already lost. The discipline has mutated 3 times in the last decade, and most CTI teams are still running a model that died in 2019. 2 stats explain why this video exists. 1. Median dwell time in 2025 collapses just 2 days. Over half of the ransomware deployments now complete within 24 hours of initial access. The question isn't, what is detection engineering? The question is whether the version you're running can fire inside an hour, because the attacker definitely can. Past, present, future. 6 phases, 2 languages, 1 pipeline, and 1 shift in 2026 that broke the whole model. There's a lot to cover, so let's get into it. Detection started as a chase. In 1971, the creeper worm propagates across ARPANET, the predecessor to the internet. Someone writes Reaper to hunt it down. Known bad? Find it, kill it. That's the entire model. It worked because there were maybe a few dozen pieces of malicious code in existence on Earth. Then, the Morris worm in 1988 broke that model. Took down roughly 10% of the internet in a single propagation event. The industry's response was to formalize certs and commercialize signature-based antivirus. Think McAfee or Avast. A signature is a hash, or a string, or a sequence of bytes. You compute it, you compare it, you alert on it. This is mathematically elegant, but operationally doomed. The 2010s changed the math for detection. Along came endpoint detection and response tools, or EDR for short. They solved one specific problem: getting structured telemetry off the host at scale. Sysmon, Windows Event IDs, process creation logs, command line arguments. For the first time, defenders could see behavior and not just artifacts. Then, in 2013, YARA gets released, a pattern matching language for files and memory. Then, further down the line, we have Sigma. In 2017 it dropped. Same idea, but applied to log events. It was vendor agnostic, and this time written in YAML. Suddenly, a detection written by a researcher in Berlin runs in a Splunk deployment in Sao Paulo. That portability looked like the answer, but it wasn't. And every detection program that bought those third-party rule packs and called it a day learnt that the expensive way. Now, a detection engineer is not a SIM administrator who just knows a bit of regex on the side. The discipline has 6 phases, and only one of them relates to rule writing. You'll find that at phase 4. So let's get started with phase 1. This is requirements and discovery. Where does the idea come from? CTI flagging APT29 using Mimikatz for LSS access? A red team engagement exposing a blind spot? Or an incident post-mortem? If your detections start with "I read a blog post," you're doing intel-driven detection wrong. No requirement means no rule. This is what most teams skip, and they pay for it later down the line. Phase 2 is triage. Not every detection makes sense. Score on a severity level, environmental relevance, and maintenance cost. A rule that costs you 40 hours a quarter to tune is a liability, not an asset. Phase 3 is investigation. What telemetry actually shows the behavior? What does normal look like in your environment? This is where most programs collapse. They build a generic detection baseline and then ship it off, resulting in thousands of false positives for their SOC team. Phase 4 is development. This is where things like Sigma for log events or YARA for files and memory come into play. These vendor-agnostic languages allow you to version control your detections and deploy them at scale. Then phase 5 is testing. You want to test your rules against historical data and simulated attacks. And this is the phase a lot of teams skip or just fly through. Then phase 6 is the final one. This is where deployment and maintenance come in. You push to production and then you use metrics to measure the success of your detections. Finally, you retire the detection when it's no longer useful. Remember, detections have a half-life, so treat them as infrastructure, not artwork. If you have a security control that covers a detection, it's far better to implement that control and save on the SIM resources, like storage and compute. Most SOCs don't have a detection engineering function. They have a rule writing function, and there's a difference. Rule writing will produce alerts. Great. Detection engineering produces measurable coverage against a defined threat model. If you can't tell me your coverage of credential access as a percentage with a confidence level, you're not engineering, you're just guessing. Here's a Sigma rule for detecting PowerShell console history clearing, a classic anti-forensics technique. That rule can be converted to Splunk SPL, Elastic KQL, Sentinel KQL, Chronicles YARA L language, and many others. You write it once and deploy it everywhere. If you can write an SQL where clause, then you can write a Sigma rule. This is your baseline. Write Sigma rules and then convert them into your detection language of choice, be it a SIM provider, EDR, or even just a login solution like Datadog. Now, why is it important to write in a vendor-agnostic language? Well, that's where detection as code comes in. Detection as code treats every rule like production software. You have a repository that's version control using Git, organized by detection type or MITRE attack technique, then a pull request workflow for every change. Within this continuous integration pipeline, you have testing. Your rule will execute against labeled test data. Known bad samples should match, and known good samples should not. You assert the expected behavior on your code. Then when it comes time to push into production, you get it peer reviewed. Another engineer reads over the rule, catches any logic errors or performance issues, and any potential evasion paths you might have missed. On merge, the pipeline pushes to your SIM via its API. Zero manual deployment. And the benefit is speed and rollback in case you get something wrong. When a rule causes a false positive explosion at 3 AM, you git revert the commit, the pipeline pushes the rollback, and you can go back to sleep without generating any more false positives. That is the engineering part in detection engineering. If your team is still editing rules in a web UI with no version control history, you are operating a 2015 program, and it's time to catch up to the 2026 threat landscape. Earlier I promised the industry had got one big thing wrong. Here it is. When Sigma was launched in 2017, the message was write the rule once and deploy everywhere. That's true at the syntax level. It is catastrophically false at the operational level. A Sigma rule for credential dumping, translated into your SIM, still depends on your log sources, your baseline, and your tuning. The portability of the language created the illusion that detection was a content problem. It is not. Every detection program that bought those third-party rule packs and called it a day learned that the expensive way. Which brings us to MGM and the MGM Resorts hack back in 2023. September 2023. Scattered Spider compromises MGM Resorts. Over $100 million in losses. Casino floors offline. Hotel keycards dead. Scattered Spider abused a legitimate Okta feature called Inbound Federation to register their own identity provider inside their MGM tenant. They weren't exploiting a vulnerability. They were using a feature. From there, they federated trust, escalated to the accounts running at the identity access management infrastructure layer, and pivoted into the VMware environment. Where was the detection engineering failure here? There was no rule for new identity provider registered in our Okta tenant, because nobody had thought of it. Because this entire discipline of detection engineering was built around malware execution on endpoints, and identity has now eclipsed endpoint as the primary attack surface. 75% of intrusions in 2024 were malware-free. Detection engineering programs without an identity-first telemetry strategy are just defending the wrong castle here, and that is something MGM learned the hard way. Now, we've got to talk about the elephant in the room here. AI and agentic detection. There are two AI conversations in detection engineering at the minute. First, we have AI-augmented authoring. This is where you use a model to draft a Sigma rule from a threat report, translate that logic across query languages to summarize a noisy alert chain. This is real and it's shipping today. A lot of teams are using this to compress that time from intelligence to time to deploy a rule by an order of magnitude. The second is agentic detection, where autonomous agents that ingest new threat intelligence, generate the corresponding atomic test, execute in a sandbox, validate whether existing detections fire, and then open a new pull request if coverage is missing. Cool stuff. This is the model that CrowdStrike and Datadog and various open source projects are racing towards. Look out for this in the future. Here's what AI doesn't change. An LLM does not know what normal looks like in your environment. Sure, it could write a syntactically perfect rule for a who am I execution, but that rule might generate 10,000 alerts a day on your jump boxes because your sysadmins run who am I all the time. The investigation phase, the environmental baselining, the false positive triage, and the is this actually weird here judgment is the part of the detection engineering lifecycle AI is worst at, because the answer lives in your data and your intuition, not in the model's training corpus. The detection engineers who lose their jobs to AI in the next 3 years are the ones writing rules from scratch. The ones who keep their jobs are the ones who can review an AI-generated rule, identify the evasion gap or performance issues, and explain it in a peer review. The skill ceiling just went up because the skill floor is getting automated. So we've covered the life cycle, and we've covered the stack that you can use to get started with detection engineering. We covered why MGM class breaches keep happening until detection programs reorientate around identity rather than malware. But there's a problem we raised in this video that we haven't solved yet. Detection without a quality threat intelligence pipeline is just guessing in YAML. Watch this video to learn more about intelligence requirements, so the rules you build are answering questions your organization actually has, and not just the ones the vendor or people online tell you to solve. Phase 1 of that detection engineering lifecycle is so important. Detection is an environment problem disguised as a content problem. Build your environment, that's the whole job.